This video introduces the dot product of two vectors. So you cannot multiply two vectors together, but you can take the dot product. So here's what we're going to say. Let's say we're in R3. We could take the dot product of two vectors, A, B, C, and put a big old dot, take the dot product with X, Y, Z. So I have two vectors in R3. The definition of the dot product is to take these two vectors, combine them, and get a real number. So I'm going to combine these two vectors and get a number out as a result. And that number will be A times X plus B times Y plus C times Z. This is how you calculate the dot product. And in this video, I'll try to help you understand why anyone would want to do this calculation. So let's do a numerical example just to make it clear exactly what's going on. So for example, I could take the vector 3, 0, 1 in R3, and I could dot it with the vector 2, negative 1, negative 1. And this would be 6 minus 0, or plus 0, minus 1. So the dot product of these two vectors is the number 5. So let's start with some observations about the dot product. Observation number 1, and this is really key. The length of a vector squared is the dot product of the vector with itself. So that might be a bit of a surprise that the dot product is actually related to the length of the vector. So why is that the case? Well, let's do the situation if we're in R3. So if I have the vector ABC, the length of the vector squared is the square root of a squared plus b squared plus c squared squared. That just gives me a squared plus b squared plus c squared, which if you do the dot product of the vector ABC with itself, this is exactly what you get. So that's observation number 1. The dot product of a vector with itself is the length of that vector squared. The next observation is if I take two vectors and dot them, it doesn't matter the order in which I calculate the dot product. So u dot v is the same as v dot u. So order does not matter when you're taking the dot product. And then observation number 3 is there's a distributive property. If I do u plus v, and I dot that with another vector w, say, then the dot product behaves as you expect multiplication to behave. You're not doing multiplication, you're doing a dot product, but it works almost the same way as multiplication. So you would do u dot w plus v dot w. I'm not going to verify properties 2 and 3, but if you just expand everything out in terms of their components, it works out pretty nicely. Okay, so you could take a dot product, but why would anyone do this? It seems like a strange operation. The main reason that people care about dot products is because of what I'm about to write down. So here is the main theorem about dot products. If I have two vectors, u and v, and I take their dot product, then it's actually turns out to equal the length of u times the length of v times cosine theta, where theta is an angle that's in between 0 and pi between the two vectors. So the main reason that people care about the dot product is because it gives you information about the angle between the two vectors. I'll do an example, and then I'll show you why this theorem is actually true. So here's an example before we explain why it works. What is the angle between, how about let's do the vector 3, 1 and the vector -1, 2. Well, over here, let's draw a picture to see if we understand what's going on. So I'm in R2, two-dimensional vectors. My first vector is 3, 1. So here's a depiction of the vector 3, 1. I chose to write the vector starting at 0, 0, but again, I could have chosen to put the starting point anywhere as long as I travel 3 units to the right and 1 unit up. I've got the vector 3, 1. Okay, the vector -1, 2 says travel -1 units in the x direction and 2 units up. So the angle theta in the theorem is actually the angle between these two vectors right here. We say that theta has to be in between 0 and pi because you want to take theta to be the smaller of the two angles, not the big way around. You want to take the smaller of the two angles. Okay, so to calculate the angle between the two vectors, here's what I'm going to do. I take the dot product of these two vectors. So I take the dot product, and I get 3 minus 1, so -3, plus 2. That's the dot product of these two vectors, 3 times -1 plus 1 times 2. So that's over here, u dot v. And that should equal the length of u. So the length of u is the square root of 9 plus 1 times the length of v. The length of this vector is 1 squared plus 2 squared, or 5. And that is cosine the angle between them. So now you could solve for theta. So you can rewrite this and you can say cosine theta is equal to -1 over the square root of 50. Then you can apply inverse cosine. So theta is inverse cosine, arc cosine, of -1 over the square root of 50, which I entered into my calculator, and I got approximately 1.71. That's in radians. So that gives me the angle between these two vectors. Okay, why is this theorem possibly true? Let me try to explain that to you. So let's do the theorem again. It's so good it's worth writing down twice. So here's the theorem. The dot product of u and v is the length of the two vectors multiplied times cosine the angle between them. So let's draw a picture to explain why this works. So here's the picture. I'm going to start with a vector u. Maybe that's my vector u. And then I'm going to put the vector v starting at the end of the vector u. So that's the vector v. The angle between the two vectors in this picture is here. That's the angle theta. The vector that starts at the beginning of u and ends at the end of v, so this vector here, that's the vector u plus v. Why? It's what I get when I start by applying the vector u and after applying the vector v. So that's basically the definition of vector addition. So here's a triangle. This is a triangle. And the triangles, here, so this is the proof of why the theorem's true. The triangles obey the law of cosines. So let me remind you of the law of cosines. If you have a triangle like this, it says that the length of this side, so the length of this side is the magnitude or the length of u, that side length squared, plus the length of v squared, so the length of this side squared plus the length of this side squared, is equal to the length of the hypotenuse squared, u plus v squared, minus 2 times the length of u times the length of v times cosine the angle between them. Now, you may not instantly remember the law of cosines, but you probably remember the Pythagorean theorem. That says if you have a right triangle, in which case this angle theta is pi over 2 or 90 degrees, then this term here isn't there. Well, if you take the angle theta to be pi over 2, cosine of pi over 2 is 0, and that term vanishes. So at least you could verify that the law of cosines is indeed correct when the angle is 90 degrees. But this is the more general statement about triangles. Well, now I'm going to take this law of cosines, and I'm going to use my first observation about the dot product. The dot product is really the length. If you have the length of the vector squared, that's the same thing as the dot product u with itself. This is the same as the dot product of the vector v with itself. This over here is u plus v dotted with u plus v. And I'm going to leave this term the same, so that 2 times the length of u, the length of v, cosine the angle between them. Now I will distribute. I will treat this term just like regular multiplication and distribute. So over here, this becomes u dot u plus v dot u plus u dot v plus v dot v. So I just distributed everything, and that's still minus this extra term, minus 2, the length of u, the length of v cosine. Now, I could take both sides of this equation, subtract u dot u. I could take both sides, I could subtract v dot v, and then I could place this on the left, and I get 2 u dot v should equal, I guess I put it on the other side so it has a negative in front as well. So I subtract this onto the other side of the equation. I get negative 2 u dot v. That should equal negative 2 the length of u, the length of v, cosine the angle between them. Well, I'm pretty much there. Now you can just divide both sides by negative 2, and I'm done with the theorem. U dot v, that's the same as v dot u, is the length of u times the length of v times cosine the angle between the two vectors. Okay, join me in my next video for a couple more examples of the dot product.